So far, the performance measures that we have described are measures that basically tell us how well a model is doing based on the data sets, training and testing data sets that we have. However, sometimes we need to understand how well our model might be performing under different settings. For example, if you think about naive Bayes, where we might determine that a sample is of one class or the other based on a given probability, we might want to set a threshold on that probability, right? And say, samples that have a probability higher than a given threshold are going to be considered of class 1 versus class 2, for example. And in this type of settings where we have a model that is based on a threshold, on a decision based on a threshold, then for those cases, ROC curves are very useful because they allow us to explore how well the model will perform given different values for the threshold. And in fact, ROC curves stand for receiver operating characteristic curves, and they are used to depict the trade-off between true positives and false positives. Okay, ROC curves were created for binary classifications, but as we will see, they can also be extended for multi-class classifications. But again, the main idea here is that for certain types of models for which we have to determine a specific threshold to understand whether it's from one class or the other, sometimes that threshold is hard for us to determine, and so a way to explore what threshold we could be assigning to that model are ROC curves. Why? Because they allow us to explore false positives versus true positives for different types of thresholds. So how well would the model perform in terms of false positives and true positives, given that we are considering different thresholds for the same model? And based on ROC curve, then we'll be able to decide what threshold is the most appropriate for the setting that we have. Okay? And this is again extremely important in settings, for example, where we have or we try to identify patients that are sick, right? And so for patients that are sick, we want to have extremely high true positives. Like we really want to identify all the patients that are sick, but we want to have extremely low false positives. So we want to make sure that we don't label as sick someone who's healthy. And so we are looking for classifiers that allow us to have like really high true positives and very low false positives. And so ROC curves will allow us to explore what are the thresholds that might give us the best combination of these two. And we'll see an example in a second. So this is, how a ROC curve is represented. On the x-axis, you have the false positive rate, which is, 1 minus the specificity. And on the y-axis, you have the true positive rate or sensitivity. And so basically what the dashed red line represents is, the random guess. So, if basically for any false positive rate that you have exactly the same true positive rate, this means that basically, your classifier is guessing. Anything that is above the line is what we're looking for. In fact, this blue dot here, the perfect blue dot, it's basically the ideal situation in which, for any false positive rate, you always have a true positive rate of 100%. Okay, so you are basically detecting all the samples that you have, but you never have any false positive. Detecting all the positive cases that you have, but without any false positive. Okay. And so that's a perfect scenario. I mean, it typically never happens, but in general, what we want to make sure is that we are in the area of, A and or C, okay? C period, okay? I mean, we want to definitely be in the area where it says better, and that's the area where we want to have our ROC curve. And so, as you can see there, in order to compute this ROC curve, we basically need to compute for a given classifier different pairs of false positive and true positive rates. Okay, so in general, when you have a classifier, you have like one true positive and one false positive rate, right? That's what we've been seeing so far. But you can actually compute other true positive and false positive rates for that same classifier by considering different cutoff points. And if we put together all those points, that's a representation of the ROC curve. So let me walk you through an example to understand better how a ROC curve is computed. Again, I mean, there are packages in R, we'll see them, that allow us to compute a ROC curve, but basically this is for you to understand exactly how do those packages work internally. And so if we have, I mean, any time that you've worked with just, any classifier that you've worked with, you have, as I was saying before, one false positive and one true positive, right? And so that would be just 1 point in the ROC curve. How is it that we compute those multiple points? Considering what we define as cutoff levels. So the example that we're going to be looking into is basically a set of patients for whom we have measures of their T4 hormone levels. Okay, the T4 hormone is a hormone that indicates whether a person has hypothyroidism or not. Okay, if they don't have hypothyroidism, this is a condition known as euthyroid. Okay, and so basically in this table, what we have is the T4 value for different types of patients. So we observe that when the T4 value is of 5 or less, in general, it looks like, that's a scenario where the patient is going to have hypothyroidism. So you see there that a T4 value of 5 or less is associated to 18 cases of hypothyroidism and 1 normal case. When the T4 value is between 5 and 7, it looks more like, it's a normal setting where, 17 patients are normal and 7 patients have hypothyroidism. If we look into values between 7 and 9, it's even more radical, so most of the cases are normal, and 9 or more similarly. Okay, so, if you have something like this, let's imagine that we want to compute a classifier that's going to determine whether an individual has hypothyroidism or not. What would be the true positive and the false positive rates, and how is it that we compute different pairs of true positive and false positive rates so that we can represent the ROC curve. And so what we need to do is basically what I said before. We need to define cutoff points. And so the cutoff points that we're going to define are basically based on the independent features that we have. In our case, it's a T4 value, right? So our cutoff points are going to be, okay, what if we consider T4 value larger than 5, or T4 value larger than 7, or T4 value larger than 9? Okay, how would that change the true positive and the false positive rates that we are getting? So imagine that we compute, T4 values of 5 or less, or larger than 5. That's our cutoff point, right? So if we consider something like that, let's say that what the classifier is saying is, okay, if you have 5 or less, how many cases we have of hypothyroidism. If you have 5 or more, how many cases we have of hypothyroidism. That's, the simplest classifier that we could be considering. And so if we do something like this, we can go back to table 1 and basically count how many cases we have with 5 or less, and count how many cases we have with 5 or more, right? And so if you come up with this table, what you can do there is compute the sensitivity and the specificity, okay? And basically those are the values that we are going to be using in the ROC curve. And this could be just 1 point in the ROC curve. But we could do exactly the same thing for T4 value of 7 or less, or T4 value of 7 or more. Okay, and if we do that, basically our cutoff point being 7, that would give us, a different set of cases with hypothyroidism or not. And the classifier here we would be doing, if it's, say, if it's smaller than 7, you have hypothyroidism. If it's larger than 7, you don't have hypothyroidism, right? And basically, given that classifier, how well are we doing? And so we would compute again the sensitivity and the specificity. And repeating exactly the same case, for the case where the cutoff point is 9, in this case, the classifier that we are building would be, okay, let's imagine that, any case with values smaller than 9 are considered that have hypothyroidism, and any cases with 9 or more are considered to be normal, right? So if we design something like that, how would our model be? Okay, and so basically by changing those cutoff points, that we can compute the ROC curve. Okay, and so, if we put together the sensitivity and the specificity values that we have computed for each of the different cut points that we have computed, and we represent those, we get the ROC curve. Okay. I mean, so the difference between this one and this one is that, basically the sensitivity, it's the true positives, and the specificity is not represented in the ROC curve. In the ROC curve, we represent the false positives, which is 1 minus the specificity. And so that's the only change between those two tables. And so these are the numbers that we're going to represent. And this is the ROC curve that we get. Okay, so how do we read this? So basically, for point 0.5, if we consider the cutoff point there, what that's telling us is that, we have very small false positive rates, which is good. But at the same time, we have very, very low true positive rates. Okay, so, I mean, ideally what we want to go for is something like go like this 1 point, or go to this corner. Basically, like, we want to be able to detect the positive cases that we have. We want to be able to determine all the hypothyroidism cases that we have, but at the same time we want to have the smallest number of false positive rate as possible. Okay, and so 5 is kind of okay. 7 is kind of an in between these two, right? So with the cutoff point of 7 is telling us is that, we have quite a very decent true positive rate, almost 80%, right? And the false positive is acceptable, around 20%, okay? And point 0.9 is telling us, yeah, we can go up to a really high true positive rate, right? Like almost 90%, but in that case, the false positive rate is going to be really high. Okay, so the interesting thing about ROC curves is that they basically also allow us to understand, what's the best cutoff point, right? So probably the more you move into that area, the higher the false positive rate is. And for something like, for example, detecting hypothyroidism, you probably want to reduce, or cancer, you probably want to reduce as much as possible your false positive rate. So, this curve allows you to understand, what's the trade-off between the different measures, and basically where do you want to set the cutoff point for your classifier. Okay, so all these things with respect to ROC curves, okay, basically, representing a ROC curve given a set of predictions and a set of labels, evaluating the different cutoff points and how, each pair of true positive and false positive rates is represented in the ROC curve, is something that can be done with a package in R, a library which is called ROC-R. Okay, and so here we're going to go through a simple example in which basically we are assuming that we have a set of predictions and a set of labels, and we're going to represent the ROC curve, okay? And then basically we'll compute, given that ROC curve, we'll compute the accuracy, and we'll also compute the area under the curve. So the area under the curve, it's basically what the name says, the area under the curve, and it's also used as a way of measuring how good a classifier is, okay? And then we'll also see how to compute precision and recall given a ROC curve. And so, let's go back here and let's cover a little bit how would these things be done in R. So let's open RStudio. I have it here. And so, as I was saying before, the first thing that we want to do is basically load the library, which is called ROC-R. And so once we have this library, I'm going to be using a data set that's available within this library, which is called ROC-R simple, right? And basically what ROC-R simple has, ROC-R simple, if you take a look at this, basically ROC-R simple contains a set of predictions, right? Imagine, that we have been working on, say, the problem of predicting the probability of something being X or Y, something being positive or negative, right? So this is a set of probabilities that we have. And their associated labels. So we have, in this case, 200 different data points, 200 different predictions, and we have 200 different labels, right? And we want to be able to represent the ROC curve. Okay, this is, again, it's a very generic case because basically depending on the problem you've been working on, your predictions and your labels will be different, okay? But once you have the predictions from any classifier you've been working with, and you have the labels, you can basically replicate the experiments that I'm going to explain here. And so, given that ROC-R simple, what basically we can do is build a prediction. So there's a prediction function, which basically, it's not implementing any prediction, okay? So the prediction function in ROC-R, what it does is a way of creating an object that associates predictions to labels, okay? So in this case, you're basically saying, okay, so these are the set of predictions that I have, and these are the set of labels that I have, Okay, we are not predicting anything. It's just the name of the method. And basically, there's a function within the ROC-R library that is called performance. Okay, and what performance does is precisely computing the ROC curve performance, and then we want to compute the performance of the elements in the prediction, and we want to represent the true positive rates versus the false positive rates. Okay, and we can basically plot the performance, and what this is showing us, as you can see here, is basically the ROC curve for this specific example, that we have with the predictions and the labels. And you can obviously, of course, as I was saying before, you can also put, the random case, which is the diagonal line here. And basically what this is telling us is that anything above this line is better than randomness. Okay, so what this is telling us is that, this classifier is doing, in certain cases, probably around this area is doing pretty well, because, we have quite low positive rates, but quite high true positive rates. Okay, this is something that, this area here is the area that we are looking for. So this is a pretty good classifier. Okay, so this is how ROC curves are computing using the package. Okay, something else that you can do with the ROC curves, basically I've written here a function for you to explore, and what you can do is try and understand, what's the best setting. Okay, so basically what this function is doing is, given all the labels that we have, all the predictions that we have, and given the ROC curve that we have computed, what's the best possible case. Okay, and basically what this is telling you, the point that I was signaling before when I was telling you, this is like 0.2, 0.8. So that's specifically this code allows you to automatically compute that point. Okay, you can run through it. Basically, the best point is the one with sensitivity 0.84, like 84% sensitivity. The specificity, remember, that is 1 minus, so it would be a specificity around like 0.15, and the cutoff point would be 0.5. Okay, so basically what this is telling us is what I was saying before, right? That the best point is somewhere around here, okay, where your true positive rate is around 80-something% and your false positive rate is around 15%. That's exactly what we are seeing here with the sensitivity and the specificity. So what this code allows you to do is to, in an automatic manner, do the inspection and basically tell you what's the better cutoff point that you could choose for your classifier. Okay, in order to get the best true positive rate with the lowest false positive rate. Other things that you can compute with the ROC-R package, we can also compute the accuracy. Okay, let's try that. So basically, to compute the accuracy, we also use the performance function, but in this case, it's specifying that we want to compute the accuracy. Okay, so the performance package is basically the package that we use mostly for ROC curves, and in this case, what we are going to do, performance is basically say that we want to focus on computing the accuracy. Okay, and if you plot that, what this is showing us is the accuracy of our model given different cutoff points. Okay, again, remember that the ideal cutoff point that we identified was 0.5, which is somewhere around here, right? And so in fact, that's the one that it's giving us the highest accuracy. Okay, remember it was the one with the highest true positive rates. Okay, so this is exactly, this is to confirm that in fact we are doing things right. And if you want to compute this point automatically, what I'm showing here, the maximum accuracy is exactly this code here, is exactly doing that. Okay, so it's basically going through all the values that we have in the accuracy performance object and basically identifying the one that has the highest Y value. Okay. And if you run this code again, you can run it at home, you will see that the outcome for this code will be accuracy 0.85, cutoff point 0.50, okay, which is exactly again this point here. Okay, the accuracy is 85 when the cutoff is 0.5, which is exactly what we showed before. And another measure that we can do is also the area under the curve for ROC curves. And so for the area under the curve, that's also another way of representing how accurate the performance of the classifier is. And so again, pred, which is the object that contains all our predictions and labels, and in this case, the measure would be the area under the curve, under the curve. Okay, and so basically, if you access the values that you have there, the y values that you have there, it will tell us that that's the area under the curve value. And what you can do with this number is basically compare across various binary classifiers and see how the area under the curve changes. So that's another way. So you could use the accuracy, you could use true positives, you could use true positives and false negatives, you could use the area under the curve, right? So these are again different performance measures that you can use in a binary classifying setting to report how well your classifier is doing or to compare across classifiers. Okay. Okay, and finally, we can also compute precision and recall. So again, the approach is exactly the same thing. We use the performance function, and you specify pred, which contains the labels and the predictions. And then in this case, you specify that you want to see the precision and the recall. And we can basically plot that. Okay, so let's go. We are going to be using the same function, performance, with pred, and we are going to be plotting or willing or interested in exploring precision and recall. Okay, and now we plot the output of that, of perf1. And basically what this plot is showing us again is the representation. Let me show this larger. The representation of the recall on the x-axis versus the precision, right? And we can see three different types of behavior here. The first behavior around this point is that we have a really high precision but extremely low recall on the left-hand side corner of the plot. What this is telling us is that, for a given threshold in the model, there's a case in which we have a very low recall, meaning that we can identify, for example, if we think about the hypothyroidism problem, in that setting, in this case, a low recall would mean that we are identifying a very small number of individuals that have hypothyroidism. But that for those that we are identifying, the precision is really high. Like overall, the model, the precision is really high because we are correctly identifying that small number of individuals that have hypothyroidism, and we're correctly determining that everybody else does not have hypothyroidism. So that's, this corner setting. If we look at the other side of the plot, it's exactly the opposite behavior. The recall here is really high, even around 1, okay, but the precision is really low. What this means is that the model, with this type of thresholding, the model could be able to identify all of the individuals that have hypothyroidism, but at the same time, the model would be predicting as having hypothyroidism a large number of individuals who don't. Okay, and so the recall is high just because in this case the model would be saying that everybody has hypothyroidism, and that's the reason why the precision is really low. The interesting part of this model is in this plateau here, right? Here we have pretty high recall values up to around 80% with pretty high precision values as well, right? And in fact, the cutoff point of 0.5 that we have been discussing is around here, okay? And what this is telling us is that there's a specific model with one specific cutoff point that allows us to have really high recalls, so we can identify a very high percentage of the individuals that have hypothyroidism, but that at the same time our model has high precision, meaning that for those that don't have hypothyroidism, most of the times we also classify them as not having hypothyroidism. Okay? And this is, the type of the area where the cutoff point that we have identified mostly lies. Okay, and so as you can see, by combining different plots in terms of precision and recall, in terms of accuracy, in terms of ROC curves, we can better understand the performance of our models, but we can also better understand what would be a potential threshold for the model that we are interested in executing. Okay, and so far we have talked about ROC curves for binary settings, right, where we only have 2 classes. However, this method of exploring, how true positives and false positives evolve for different thresholds is a method that can also be used for multi-class settings. Okay, in fact, if we are interested in understanding what threshold should we put in our model for it to work well, we would also like to do that ideally in multi-class settings. And so, that's the reason why most packages will allow you to do that as well. And so the general approach for this is the compute one versus all approach, again, where basically, we compute one ROC curve for each one versus all. So for example, if we have, say, three different classes, we would have one classifier for class 0 versus 1 and 2, another classifier for class 1 versus 0 and 2, and a third classifier for class 2 versus 0 and 1. Okay, and then basically we could either represent one ROC curve for each of the one versus all classifiers, or we could also compute macro or micro averages. The macro average, it just takes the individual true positive measures and averages across all classes. The micro average basically weights by the number of samples that we have. Again, similarly to the F1 score that we discussed, the micro average is advisable for imbalanced settings where one of the classes might have a larger number of samples. And so, for example, this is just an example of multi-class ROC curves where we have three different classes. You can see here that we have the results for the ROC curve for class 0, where we are classifying whether a sample is of class 0 or not, and that not could be class 1 or 2. The yellow curve represents a ROC curve for class 1, so it's either class 1 or 0 and 2. And then the blue line is a ROC curve for class 2, which is either 2 or 0 and 1. Okay, and then we have two dashed lines. The two dashed lines represents the macro and the micro averages for the three ROC curves. Okay, so if we were to discuss the results for this setting, we could either show the ROC curves for the three different one versus all classifiers, but we could also present the micro or the macro averages. As you can see, the macro average is just an average value for the three different true positive rates that we have, whereas the micro average is weighted by the number of samples, and that's the reason why it's slightly worse. What this is telling us is that highly probably, there is one class that has a higher number of samples and that it's not performing as well, and that's the reason why the pink line, the dashed pink line, is slightly below the dashed blue line. Okay, and finally, I've been using the ROC-R package. You can find more information in that PDF file. There's also another package that I haven't discussed, which is called PROC, but that I also encourage you to explore for different types of performance and ROC representations that you might be interested in doing for your milestones.